Hi, and welcome to another in a series of videos to accompany a reading course in Probability Theory, the Logic of Science by Edwin Jaynes. This lecture will cover the material from chapter 1 of the book called Plausible Reasoning. In the last video I talked some about the history of probability and statistics, and in particular the disagreements about the interpretations of probability and the way that probability is used, practically speaking. I described the program of Jaynes's book, which is going to be to take probability and put it into a logical context as an extension of what we kind of think of as ordinary deductive logic. So in particular, the kind of main result of the book is deriving the ordinary rules of probability, the kind of mathematical axioms of it, as consequences of some more fundamental criteria for consistent logical reasoning in the circumstance of limited information or reasoning with incomplete information. I didn't mention it in the last video, but Jaynes actually attributes this idea to a combination of the work of two different authors. So in particular, someone named R.T. Cox, a physicist, and a mathematician named George Polya, who wrote extensively about the ways that mathematicians reason and kind of come up with ideas. The theorem in particular that we're going to talk through this time and next time, if you are looking for more information about it and you look up Cox's consistency theorem, I think you'll find essentially this proof. Okay, so this isn't all original to Jaynes, but it is basically a combination of these two authors who came before him. So, as I said, that argument will take place basically over the next two chapters of the book. In the first one, we're going to get to the qualitative considerations, the kind of criteria that we look for in consistent reasoning about incomplete information. In the second chapter, we actually then put those into quantitative terms and get to the rules of probability theory. Okay, so chapter 1, we're talking about plausible reasoning. And Jaynes introduces this idea of plausible reasoning by way of an example. So the example is, imagine that a police officer is out patrolling the streets one night and he sees a jewelry store with a broken window and a man sneaking around wearing a mask and carrying a bag of jewels from the store. The police officer is naturally going to conclude that it's likely that that person is a thief and has just robbed the store. Okay, so that seems like a reasonable kind of thing to conclude, but as Jaynes points out, and as I'm sure has been kind of the basis for legal defense many times, that conclusion is not actually logically deductive, meaning that it's not somehow derivable from first principles that this person has to be a thief, just based on what we've observed. And the way that you can kind of see that is you can imagine other possible explanations that would get you to that same circumstance. So, maybe, for example, this guy is the owner of the store and he just happened to be out one night at a costume party and he was dressed, in a mask, and he was on his way home from the party and he saw that the window of the store had been broken and he thought, okay, I better go in and gather up all the jewels and take them out of the store just for safekeeping, right? So that's a very unlikely scenario, and we probably would have a hard time imagining that, but it's not inconsistent with logic, and so we can't discount it as a possibility. So the basic idea is that in kind of our daily lives, we're using this sort of reasoning all the time, right? So we make some observations and we take action based on some guesses we have about what those observations mean, but we're not necessarily deriving things deductively. So, for example, we look out the window, we see that it's cloudy outside, and we decide to take an umbrella with us when we go because we think it's likely that it's going to rain. Or we feel some pain and we say, okay, I better go to a doctor and get this checked out because there could be something wrong, but it's not, again, a deduction. So this sort of reasoning with incomplete information is just something that comes very naturally to us and something that we're very familiar with. Okay, so when we talk about deductive logic and deductive reasoning, really what we mean by that is usage of the strong logical syllogism that originally goes back to Aristotle. And that basically just consists of the following kind of steps of logic. Okay, so this is going to be a basic deduction. We have what's called the major premise, so we'll just think of that as our assumption, that if some condition P is true, then it must follow that Q is true, and Q is true. Okay, then we have some observation, which is also called the minor premise, that we see that P is true, and we conclude that Q is true. Okay, so basic example of this that goes back to Aristotle would be to say, all men are mortal. So in other words, if someone's a man, then that person is mortal. Socrates is a man, therefore Socrates is mortal. Okay, so if P then Q and P, therefore Q, basic kind of logical deduction. The contrast to this, okay, what we're going to talk about in plausible inference would be to say, okay, so maybe we'll have the same kind of assumption. If P is true, then Q is true. But instead of observing P, what we're going to assume is that we actually observe Q. Okay, so we observe that Q is true. And our conclusion is not going to be that P is true, but it's going to be that P is somehow made more plausible. Okay, so let's just put that in quotes for now because we don't necessarily know what it means. But you can see right away that we're not doing the same kind of reasoning as logical deduction, because it wouldn't necessarily follow, let's say that P is true. That would be logically arguing the converse of our assumptions. So for example, it would be like, you can easily think of a counterexample, like if let's say all bats are mammals. So if my friend has a pet and it's a mammal, therefore can I conclude that it's a bat? Well, obviously not. The logical implication doesn't go that way. But what I can conclude is maybe that it's more likely that it's a bat. So it's kind of like, you can imagine, we're playing 20 questions and I'm trying to guess, what kind of animal is it? And I say, is it a mammal? And they say yes. Well, then whatever kind of assignment that I make to the plausibility that it's a bat has to be increased, by that assumption. So it's basically to say that, I don't necessarily know that P is true, but I know that one of the possible consequences of it being true has been verified. It's sort of passed that test by observation. And this is the kind of reasoning that we use all the time when we are kind of testing hypotheses or imagining conditions and then sort of testing them against what we observe. And in fact, what we're going to do is relax this a bit to say, not only can we have kind of as our major premise or our assumption that if P is true, then Q is true, but maybe even that Q is plausible, okay, or likely. Okay, so this kind of fits the example of the police officer and the jewelry store, where the assumption or the condition P is that this guy's a thief, and what we kind of assume as our major premise is that if he's a thief, it's not necessarily the case that he would be acting the way that this person is observed. Maybe thieves could act some different way, dress differently, or whatever it is. But it's kind of likely, or it's plausible that a thief would be wearing a mask and be sneaking around late at night, and that's what we observe, right? So our conclusion is that hypothesis about him being a thief is made more plausible by that observation. So although that seems like a very kind of weak logical framework, it's actually, in this example, makes perfect sense and something that we would take as a very kind of strong conclusion, or at least we would believe that as a method of reasoning. And what Jaynes points out is that actually, so this form of the argument that we've said here, that if we have our hypothesis, major premise, and we make some observation of data or evidence, it's not necessarily the case that we will conclude that hypothesis is made more plausible by that evidence. In fact, it's all kind of conditional on some amount of background information that we have about the world and the way things work. So, for example, this police officer makes this inference based on a lifetime of dealing with people sneaking around and breaking into jewelry stores. But if it were the case that, let's say, this happened every night and it was always some innocent explanation, like it was always the store owner coming home from a costume party, then over time that would kind of weaken the strength of this inference, and we might not even be led to think that this hypothesis about him being a thief is made more plausible based on the observation. So really, in the end, we'll get to this when we have kind of Bayes' rule and the quantitative probability rules. Whether evidence kind of makes a hypothesis more likely really has more to do with what other hypotheses are out there that might explain that evidence better, and what kinds of prior probabilities we put on those hypotheses. Okay, so we'll get to all that. So the kind of goal of the book, the way that Jaynes kind of lays this project out, is going to be to program a robot to reason this way. Okay, so basically to codify these kinds of inferential rules in some formal system. And I don't think we necessarily need to think about this as programming a literal robot, but maybe just kind of writing these things down in a way that we can all understand them, and we can describe them quantitatively and examine their conclusions formally. Okay, so to begin with then, we have to think about what are the kinds of statements that we want to allow this robot and ourselves to reason about. What are the kinds of propositions that we want to come up with plausibility assignments for? So Jaynes talks about a couple of statements that we might agree with just as people, but we don't necessarily want our robot to have answers to the question of how plausible they are. Okay, so the couple of statements that he gives are, first of all, say Beethoven and Berlioz never met. It's one statement, and the second statement, which I'll just paraphrase because he writes it a little bit longer, is to say that, let's say, Beethoven was a better composer than Berlioz. So the first one, we don't necessarily know the answer to that question. It's kind of possible that they did meet each other, wouldn't be inconsistent. We don't have evidence either way. But what we believe is that this is a statement that has a definite truth value, whether we know what that value is or not. Okay, so it's a clear logical statement. All of the terms in it are definable, and it has some truth value, either true or false. But the whole point is we don't necessarily know which value of true or false it is. The second one is more subjective, and even with an infinite amount of information, we might not be able to settle the question of who is a better composer, but maybe we agree with it in some sense, or as people talking in conversation, we would make such statements. But we're not going to ask the robot for plausibility assignments for this kind of statement. We're also interested in building up kind of combinations of statements like this and kind of compound logical statements that might involve more than one proposition at a time. So, for example, we might want to say, okay, what's the plausibility that Beethoven and Berlioz never met, and that there was life on Mars 5 billion years ago, and that it's going to rain tomorrow? Okay, so each one in isolation we might have plausibilities for, and what we really maybe want in the end is some joint plausibility for all of them together. And part of the advantage of using these kinds of statements, clear logical statements with a true or false value, is that we have a very nice kind of notation and a sort of arithmetic of combining statements together that we're going to be able to take advantage of. Okay, so Jaynes does a little bit of a review of this, and I'll just kind of write some about it now. The basic idea is statements, propositions are going to be represented by these capital letters. Okay, that's just our notation. And then we're going to have some other notations for ways of manipulating those statements or forming other statements based on them. Okay, so first of all, let's say we have a statement A, right? Then we're going to have the statement not A, which will denote A bar. So that's not A. And this is the one that is true if and only if A is false. Okay, so far so good. So it's just the complement of it. If we have, let's say, another statement B, then we can have A or B, which will denote A plus B, and this is the one that is true if and only if A is true or B is true. So just what you think. Okay, and finally we'll have the statement A and B, which will denote A, B. Okay, so this is going to be true if and only if A is true and B is true. Okay, and a handy kind of way to summarize that is in what's called the truth table. So let me just write this over here. So imagine that we have our kind of truth values of A and B, and they span all the possible values that they can have. So maybe they're both true, or A is true and B is false, or A is false and B is true, or they're both false. Okay, all of the possible combinations. Then, in particular, this statement not A is just going to have the opposite truth values of A, so it's going to be false when A is true. Okay, A or B is going to be true when one of them is true. Okay, so it's true here, here, and here, but false here. And A and B is going to be true only when they're both true together. Okay, so it's just going to be true in this circumstance. Okay, so these are basic kinds of ways of manipulating and combining propositions. Jaynes thing, it goes through this kind of derivation that is just standard propositional logic stuff, that actually any other possible combination that we might want to express in terms of propositions A and B, we can write as some sequence of these two together, right? So if we had, let's say, very complex statements like A implies B, and or one of A and not B, or some kind of long complex statement, their natural question is, well, how many of those do we have to worry about? What's the kind of universe of possible combinations of statements? And what Jaynes shows is that actually you can always break any such statement down into sort of finite sequence of or and not. In fact, you can do even better than that. You can have just and not. Or you can even do one operation which is called NAND. Those of you who have done symbolic logic will have seen that. But it doesn't really matter. And the basic kind of argument for that, probably not worth going through too much, but it's to say, okay, imagine that we had, some mystery function. Let's just write it down here. So let's say, again, we've got these 4 possible combinations of A and B, and we've got some mystery function which takes some truth value on these 4 combinations. Okay, so we don't know what it is. Okay, but we know that we can evaluate it once we know the truth of A and B. So the question is basically how many such functions are there that we could construct, and you can basically just sort of count them all out if you think in terms of the truth table. So we have 2 choices for this scenario, we have 2 choices for this one, 2 for this one, and 2 for this one. So we have 2 to the 4th power possible different functions, and what that means is that there's basically only that many possible statements, and you just have to kind of believe or write out that you can get each one of those as some combination of ands and nots. Okay, so again, it's all pretty standard material, but just by way of review. Now, the reason that is actually important to us, and why we actually care about it, is that in the next chapter we're going to be talking about quantitative rules of probability, meaning the basic kind of mathematical axioms of manipulating probabilities that will take the form of probability of a joint event like A or B, or the probability of A and B. We're going to be interested in these numbers as functions of, or as consequences of, probabilities related to A and B, etc. And so kind of lesson of this argument is that actually once we've got these rules worked out, that's all we need to have, right? So we'll be able to, in principle, figure out plausibilities or probabilities for any kind of complex statement that we can write down once we have the building blocks of A or B and A and B. Because that's where this is going, so if you just want to kind of have that in the back of your mind, it's probably helpful. Okay, so once we have kind of an understanding of our notation for propositions and the kind of basic arithmetic of propositions and the rules that these things obey, the next thing then to do is to write down the qualitative considerations that we want this plausibility robot to satisfy. Okay, so let's get into that now. So the idea here is that, again, we want our robot to give us back the plausibility for any kind of logical statement that we give it. And what we kind of desire is that those plausibility assignments are subject to a few just kind of common sense and generally agreed upon rules of logical reasoning. Okay, so these are what Jaynes calls the desiderata, just meaning the things we want, basically. Number 1, we've already talked about, which is just that plausibility is a real number. Which I think is already kind of naturally implied by the ways that we've been talking about plausible reasoning. When we say things like something is made more or less plausible, we need a way of comparing plausibilities. Okay, so it can't be the case that plausibility is some multi-dimensional thing where it's not clear how to compare it, or that it's based on kind of intervals where it's in a range of something and we can't compare it to intervals. It actually has to be kind of a single real number. Jaynes mentions that obviously that's not a complete picture of real human cognition. If we think about the ways that we respond to and think about propositions, we obviously have many more dimensions to that than just how plausible we think it is. We also have the dimension of how we feel about it, or so on and so forth. But in this case, all we're trying to capture with this robot is the kind of emotionless dimension of just how plausible we think the statement is. Okay, so plausibility is a real number. Greater plausibility is going to correspond to a larger number. Okay, so that's just kind of a convention that will help orient us in terms of which statements are more or less plausible. And I think it's already kind of present in the discussion we just mentioned, but any of these plausibility numbers are going to be dependent on some amount of background information. Okay, so we're going to have a notation that Jaynes introduces here called A stroke B, or A given B, which means the plausibility of A given B, or A conditional on background information B. I don't love this notation. I think that it's a little bit confusing to not have some operator here. Basically, in the next chapter, we're going to put a P in front of this, and we're going to be talking about conditional probabilities. But for now, we'll just leave this as the notation for the plausibility of the statement A given the statement or assumption B. That's condition one. Condition two is just going to be something a little bit more general, that this plausibility reasoning agrees with common sense. Okay, so this is made a little bit more precise in the next chapter, but what we mean here by agreement with common sense is really a qualitative agreement, meaning how do plausibilities increase or decrease in some particular situations where we assume information or assumptions are getting updated in a particular way. Okay, so the example that Jaynes gives is pretty general example is, if we have, let's say, A given C, okay, the probability or plausibility of A given background information C is less than the plausibility of A given C prime. Okay, so we assume that our information has been updated in such a way that proposition A is made more plausible by it. And we have that, say, proposition B is unchanged, or at least made, let's say, has the same plausibility based on the combination of A and C, or A and C prime. Okay, then it must be the case that the joint proposition AB is at least made no less likely. Okay, so we'll just say it's got to be at least as plausible as it was before, and maybe more plausible. Okay, so that's a basic kind of qualitative consideration, and it makes sense if you just kind of think through some examples. So you say, all right, I've got something I'm wondering about, and I got some new information that maybe makes that thing seem more plausible. This other condition that's somehow not affected by this new information has the same plausibility, and now I want to ask the question, all right, so both of them together, what's my estimation of it? Well, both of them together depends on some way on these two ingredients. One of them's been made more plausible, the other one's the same, so it should make sense that together that plausibility is at least not decreased, maybe made more likely. The second kind of version of that, or let's go over here. The third desideratum then is that these plausibilities should kind of we should be able to interface with them in a reasonable way. Okay, so we'll put this over here. And the basic kind of description of this is that the robot reasons consistently. And what consistent reasoning means, we'll write down in a few kind of subcases. So for the first one, we'll say if we can reach a conclusion in more than one way, if we reach, let's say, a conclusion in more than one way, we always have to get to the same plausibility assignment. So basically it's to say that if we have some complex logical statement that we're trying to assign a plausibility number to, and we can break that down into a number of stages and say, okay, plausibility of this, and then plausibility of the next thing conditional on that, and then so on and so forth, and we get to the conclusion. If we can do that along many different kind of paths to the conclusion, we always have to get to the same number in the end, which it kind of makes sense. So we don't want our answers to be contingent on the ways that we worked our way through the logical sequence to get to the answer. Part B of this is to say that we always use all of the available information meaning that whatever's been programmed in as an assumption in the plausibility problem, we're not going to just selectively ignore parts of it as we see fit. I mean, we have to kind of always keep that all in mind. The way that this is ultimately used later in the book is that Jaynes will look at basically the mathematical rules that we can derive from this, and then he'll take some other examples of things that people have tried to write down just kind of like ad hoc and say, well, what if probabilities behaved consistently with this equation? What's wrong with that? And Jaynes will basically come back to saying that it's inconsistent with this criterion, so that in some way there's been some information that was present in the problem you can identify that you've thrown away somehow in coming up with your probability assignment, and that violates this basic kind of condition of using all of the available information all the time. And the third one is a little bit trickier, which is to say that equivalent states of knowledge should give us the same plausibility number. Okay, so just remember that again we're building this robot, this machine, that we give it a logical statement, it gives us back a number, and the condition here is that if we ask it for two plausibilities that are in some sense based on propositions that the robot can't distinguish from each other, so they're equivalent somehow, then it has to come back with the same number for those two statements. So basically it's a kind of symmetry condition having to do with situations where we haven't given the robot enough information to distinguish one proposition from another one. So let's say, for example, that we just gave the robot some basic knowledge about people's names or people, and we said, okay, give me the plausibility that someone named Alex can dunk a basketball. All right, and so that's fine, the robot can give us that number, and then we say, okay, give us the plausibility that Ben can dunk a basketball. If the robot doesn't have any information that allows it to distinguish between this person Alex we're talking about and this person Ben we're talking about, it just knows that they're people and that these are people's names, then it has to come back with the same number each time. No matter what number it comes up with, it's got to be the same. If it later turns out that the Alex we were talking about was in the NBA and Ben was Ben Franklin, then it's going to come up with different plausibility numbers about them being able to dunk. The kind of technical thing that this is going to lead to in the next chapter actually is something called the principle of indifference, that basically says that in these situations where we are indifferent to multiple different propositions, we don't have information to distinguish one from the other, we have to assign them probabilities that are equal to each other, and if they kind of span the universe of all possible things, then those probabilities have to add up to 1. So it's going to be things like, why is the fair odds of drawing a ball out of an urn equal to 1 over the number of balls in the urn, just comes from our kind of indifference or our inability to distinguish the information we have about one ball being drawn out versus another. Okay, so we'll get to that next time, but that's this is actually kind of the main thing that allows us to kickstart any calculation of probabilities and sort of assign numbers to real statements. So that's it. So these are all of the desiderata. It's a little bit maybe surprising that, having written these things down, that this is all that we need to derive the mathematical theory of probability and then the probability axioms that we're familiar with. What we're going to get into in the next chapter is to actually see how these get put into practice. At the end of the first chapter, there's a little bit kind of an aside about problems of English language, and in particular applying questions of plausibility to English statements, statements in English language that have the verb is in them or the verb to be in them. So Jaynes calls this the mind projection fallacy, which is right up here. Mind projection fallacy, and the way he describes it, it's a confusion basically of ontological statements with epistemological statements. So it's if we get confused about saying if we say X is Y, are we talking about its true nature is Y, or are we saying that we perceive it to be Y? So is it an ontological issue or is it an epistemological issue? He gives a couple examples of this. Where this actually is going to come into play is in probabilities. If we say that the probability of an event is X, is that somehow a real physical property of it, or is it a number that reflects our understanding of it? Okay, so that's what the mind projection fallacy is going to be about, and we'll get to that again later in the book. That's the mind projection fallacy. We're going to see some examples later on where that really comes into play in talking about probabilities and our perceptions of probabilities, whether they are kind of real physical ontological issues or whether they are epistemological. And in summary, we have consistent logical reasoning. We have our kind of qualitative concerns for what reasoning is gonna look like, and we have some assumptions about the numbers that we're going to use and a basic kind of arithmetic of combining propositional statements together. So, as I said, in the next chapter, we're going to derive the mathematical axioms of probability theory. We're going to define what we mean by probability. And we're going to show how these probability rules then allow us to compute some real probabilities for actual problems, and in particular how they deal with combining logical statements and putting propositions together. Okay, so that's next time.